Hello everyone, I am Dr. Avradip, Assistant Professor of Physics working in Narjol Raj College. Today, the topic which we will be going to discuss is about heat engines and heat refrigerator, which is actually coming in the context of second law of thermodynamics, which is included in the core course of C6, which is included in the syllabus of third year honors physics honors. So let's start with about what is known as heat engines. So heat engines. But before we start about talking about heat engines, let me tell you about something about the second law of thermodynamics. Second law of thermodynamics actually tells us about the conversion of the energy from one form to another form. In specifically, for example, the form which we are talking about in thermodynamics is thermal in nature. So it's basically the conversion of the thermal energy into another form. For example, it's a mechanical form or the work done or something else, and vice versa. So in the context of the conversion of those kind of the energy from another form to another to other form, the kind of devices which will be coming across is one of them is called heat engine, the other will be called heat refrigerator. So let me start with talking about the heat engine. What is exactly a heat engine is and how does it work? So heat engine is basically a device which basically transforms, as I already have said, it basically transforms the thermal energy or heat into a equivalent amount of mechanical work. So how does it work actually? So in order to do that, let me draw this diagram. So it basically works into inside something called a hot reservoir. It's basically a thermal reservoir which is having a very large amount of heat. That's what I'm saying. And the only reason this particular thing is called reservoir, it means theoretically it is having an infinite amount of thermal energy. So even if you are drawing some finite amount of heat or thermal energy from this reservoir, the total amount of the temperature of this is not going to change. It's not going to increase or not going to decrease. That's why this kind of system is called a reservoir. And now just because the temperature of this one is very high, it's called a hot reservoir, or sometimes some people call it a source. In some books it's written as source, and the other one I will be calling as a cold reservoir, again cold thermal reservoir, or sometimes it's called as a sink. So it's again a thermal reservoir, which means if you take out some amount of heat or if you give some amount of heat, the temperature of this particular system is not going to change. So it means hot, that the temperature will be higher. So let me tell that the temperature of this hot reservoir is called T1 in Kelvin scale, and the temperature of the cold reservoir is known as I'll call as T2 in Kelvin scale. So what does the heat engine do? It basically operates in between the hot reservoir and the cold reservoir. So it basically does, so this is basically the engine. So it basically takes out some amount of heat from the hot reservoir, which I am calling as Q1. Then it performs some amount of work which is represented as the output of this engine. I'll call the mechanical output the work as W, and the rest amount of heat it basically gives away to the cold reservoir, which I am denoting as Q2. That's basically the simplistic picture of a heat engine, as simple as that. Now question comes, first of all, this particular engine, we know that it will be working in a cycle. So how does this particular these three parameters Q1, Q2 and W, they are connected to each other? So in order to do that, we'll be using the first law of thermodynamics, which basically states that the energy cannot be created or it cannot be destroyed. It's basically constant. So in another way, in mathematical form, we write it as delta Q is equals to delta U plus delta W. That's what we have seen from the first law of thermodynamics. It is basically the change in the thermal energy or heat, or it's the heat transfer amount. It is the net change in the internal energy of the system, and it is basically the work done on or by the system. So for our case, heat engine is basically the system. The amount of net heat flowing into the system will be nothing but Q1 minus Q2, because it's the Q1 heat is coming into the system and Q2 amount of heat it's giving. So the net heat which is coming inside the system will be Q1 minus Q2. Now, because after one cycle, as we will see shortly, that in one cycle the system comes back into the original form, so there will be no change in the internal energy, because it will come back to the same situation. So the net change in the internal energy will be 0, as simple as that. And what will be the delta W? Delta W is basically nothing but the work output which we are talking about here, which is nothing but W. So all we get is basically, it's very simple, that Q1 minus Q2 is equals to W, as simple as that. As that we would have expected, because it's nothing but the conservation of energy. Now question comes that how we actually quantify the performance of this kind of heat engines. So in order to do that, we have one particular parameter which characterizes how good the heat engine is. So for example, if we are having two heat engines working together inside the same two reservoirs, hot reservoir and cold reservoir, how do we conclude which one is working better? So in order to do that, we have one particular parameter or a variable which quantifies the performance of this heat engine, which is known as the efficiency of the heat engine. Efficiency of the engine. Efficiency. So that will be described by the symbol eta, Greek symbol eta. And the way we define the efficiency of the engine is, it is basically the mechanical output or the work output and the heat input, as simple as that. It's basically the output by input kind of a system. So work output we know, as already we have seen in the previous diagram, which I just removed or erased. It will be just simple W, and the heat input is nothing but, effective heat input is nothing but, it's the Q1. And already from the first law of thermodynamics we have seen that W can be written as Q1 minus Q2. So effectively the efficiency can be written as Q1 minus Q2 by Q1. And so let me rewrite it again freshly. So it will be, eta will be W by Q1, so Q1 minus Q2 divided by Q1, so it will be 1 minus Q2 by Q1. So that's the expression of the efficiency of the heat engine, one heat engine. So this formula clearly tells us, it's telling us a few things about the heat engine. Number one, the maximum value or the highest value this eta can achieve will be 1. It can't be more than 1, as simple as that, because Q2 and Q1, the magnitudes of those one, the sign of those things will be positive. It can't be negative or something else. So if that is the case, the maximum value it can achieve will be 1, and that's only those cases where Q2 will be absolutely 0 or Q1 is very very large enough so that we can neglect this particular ratio in comparison to 1, and at that point of time eta max can go to 1 or 100%. So in real sense, no heat engine actually can have an efficiency of 100%. It has to be always less than that. Okay, so with this, now we'll be going into the definition of something which works exactly the opposite, which is known as the refrigerators or thermal refrigerators. So a refrigerator or refrigerators, whatever. So now we need to know what exactly a refrigerator is. A refrigerator works exactly opposite to the way the heat engine works. So again, I'll be drawing something called the hot reservoir or the source, and the cold reservoir. So hot reservoir is sitting at a temperature, again T1, I'll write it at T1. Cold reservoir is sitting, or it's known as sink, it's sitting at temperature T2. So T1 will be always higher than T2. Now the refrigerator, what it does is, so refrigerator is this system. Again, it's working in between hot reservoir and cold reservoir. So this is refrigerator. Refrigerator, what it does. Now the way it actually refrigerates, that's why we have like in household we have something called the fridge, what we call usually. That's nothing but the refrigerator. Now how it works actually. So it basically takes some amount of heat from the cold reservoir. So it's basically the thing which it has to keep cool. So that's why it takes away some amount of heat from the cold reservoir. So it takes away the heat and so that it remains cool. But then what it does, some amount of work needs to be done on the refrigerator because it can't work without any external work. So and then it converts the total amount of heat Q1 to the hot reservoir it gives away. So in normal cases, household cases, basically the whole environment or air or something works as the hot reservoir basically because the heat is being emitted or radiated in the environment. So the environment works as the hot reservoir in this particular case. So in this case also, as we see that it's again the conversion of the mechanical work into heat, exactly opposite the way the heat engine works. And here also using the first law of thermodynamics, we'll be seeing that W will be written as it's the difference between Q1 and Q2. That's all. It's very easy to derive this one. But again, in order to quantify the performance of the refrigerators, we have another kind of a parameter which is known as coefficient of performance. I'm sorry, it's called coefficient of performance. Coefficient of performance. And generally it's denoted with the symbol omega like this, and the way it's defined as it's basically it's the heat taken from the sink divided by the work input, as simple as that. So it's the heat or thermal energy taken from the sink divided by the work input, and as we have shown in the particular diagram, so it will be heat taken from the sink will be Q2 and the work input is W, and again W can be written as Q1 minus Q2. So in terms of Q1 and Q2, the coefficient of performance of a reservoir can be written as Q2 divided by Q1 minus Q2. Okay. So now the question is, out of all these kind of heat engines or refrigerators, which one works the best? Which one performs the best? So we have got an answer, and the answer is, so the heat engines or the refrigerators which follow the Carnot cycle, that one will be having the maximum efficiency because that will be the that will follow the reversible process. Now in order to do that, in order to go into the performance of the Carnot engine or something, we have to see how the Carnot cycle is, how we define the Carnot cycle. So let's define the Carnot cycle. It's basically a reversible cycle of the heat engines, and the way the Carnot cycle is defined, and it's the reversible process can be depicted in a PV diagram, but let me tell you all the 4 steps which comes in the cycle, the Carnot cycle. Let me give you the details of that. There are 4 such steps. So the first step will be, it's isothermal expansion. So I'll take an example of a hydrostatic system basically. because that's the usual thing. Hydrostatic system means it's an ideal gas which has been confined inside a cylinder with a movable piston, and we'll be assuming that there is no such friction, no friction is coming into play when we are moving in, the piston is moving inside that, or it's being taken out. So now what is happening, the isothermal expansion means, first of all we are having again the hot. So I'm not writing the hot reservoir, I'm just writing hot and cold just to. So hot reservoir is having the temperature T1, cold reservoir is having the temperature T2. In the first step what happens, this particular system, it's being expanded like this. So this is the piston, so the gas is inside here in the cylinder. Now it's the isothermal expansion, and expansion is happening in the temperature T1. So this is being expanded, the gas is being expanded, so the piston is moving out, and because the temperature is kept at constant value T1, some amount of heat is being taken from the hot reservoir as expected, and will denote that the amount of heat it's taking is Q1. That's the first step of the whole cycle. Clear? Now the second one step is again the expansion followed by the isothermal one, and that in that step we will do the adiabatic expansion. So there is no exchange of heat here, because we all know that adiabatic process is a process in which there is no exchange of heat is happening with the system, with the surroundings. So no heat can go out, no heat can come in. So that means, but still it's an expansion. So what is happening? Now the hot reservoir is being detached. The piston, the cylinder is somewhere here. Still it's being expanded here like this. Initially it was having a temperature T1, now it's being expanded. There is no exchange of heat which can come. Now because the gas is expanding, some has to pay the amount of work, in the price of the work, what is happening. So that will come from itself. So the temperature of the system will go down as expected because it's expanding adiabatically. So the temperature of the gas cannot remain at T1. So now what is happening, the gas is expanding and we will allow the gas to cool down up to a temperature T2. So slowly as it's expanding adiabatically, the temperature of this system will come down from T1 to T2, and then as soon as it reaches T2 will stop. Clear? So that's the adiabatic expansion. Now what is happening? Now we will do the third step. The third step is, now we will start the compression. The first compression will be isothermal compression. Isothermal compression. So here what will be happening, now the gas has cooled down to a temperature T2, exactly to the cold reservoir. So it means it's now sitting here in the thermal contact. Now we'll allow the gas to compress, but the temperature will remain the same at T2 because it's an isothermal compression. So because we are compressing, some amount of heat has to go to the cold reservoir, and that we'll call as Q2 as we have defined earlier. So Q2 amount of heat is going into the cold reservoir here, so that it's the gas is being compressed. So that's the third step. And the fourth step will be, as you might have already guessed it, that the fourth step will be nothing but adiabatic compression. So after followed by the isothermal compression, it will be adiabatic compression. So it means now the gas has already compressed a little bit isothermally, then the rest compression will be done adiabatically. So now there is no exchange of heat that is possible. So again the gas cylinder somewhere here, and I'm still compressing the gas, so the piston is going into, but again because it's adiabatic compression, no heat can come in or no heat can go out. So basically as I'm compressing the gas, so the temperature has to increase, and so the temperature will slowly start increasing from T2, and will keep on doing the compression until the temperature of the gas reaches T1. As soon as the temperature reaches the value T1, will stop the compression. So that's how all these 4 steps are defined in the Carnot cycle, as simple as that. So 2 steps of expansion and 2 steps of compression. Now let me describe all the 4 steps in the PV diagram or the phase diagram. So this is the phase space of the hydrostatic system. In this figure, in the y-axis, I am plotting the pressure of the system. In this figure, I am plotting the volume. Now what is happening? So let me start with the point, say for example point A. The system is at point A where the pressure is PA, and correspondingly we can say the volume is VA. So the first thing what is happening is the isothermal expansion. So it will follow some isotherm, as we call it, isotherm. It has to follow an isotherm. It will reach a point B where definitely I have expanded it to go up to a volume, say for example VB, and the corresponding pressure has come down to PB. So in the whole process, the system initially was at temperature T1, and in the final step as well, when it has reached the point B, the temperature will remain T1 because it's nothing but isothermal expansion. Now we'll allow the gas to expand adiabatically. Now because adiabatically the temperature will not be the same, the temperature has to go down, and we all know that adiabates are steeper than the isotherms. So now it will expand, but in a much steeper way. So it will be coming down something like this, following an adiabate, and it will somewhere reach, for example, a point C, so that the second step is completed, the adiabatic expansion, so that the pressure goes down to PC and the volume will still increase up to VC. So this is the isothermal expansion, this is the adiabatic expansion. Now comes the both the compressions. The first compression will be, as we have already seen, it's the isothermal compression. So the gas will come back isothermally. It will again follow an isotherm. So I forgot to tell you that meanwhile it was going from B to C. The temperature has dropped down from T1 to T2. The temperature has come down to T2 over here. So when it will come back at the point, say the last point D, the isothermal compression will be completed, so that the pressure will be somewhere at PD, and the volume it will be having is something called VD, somewhere here. Maybe the pressure will go up a little bit. I think it will be above PB. Yes, it has to be somewhere here. And the last step will be again the adiabatic compression after the isothermal compression. So the temperature has to increase now. So the volume will compress from VD to VA, and it will again go back to the original position, and also the temperature will meanwhile raise from T2 to T1. With this, all the 4 steps of this particular Carnot cycle will be completed. Now let me, now the task is to calculate the performance, the efficiency of the Carnot engine. The engine which will be performing through following the Carnot cycle will be called as a Carnot engine, and the refrigerator which will follow the Carnot cycle will be called as Carnot refrigerator. So the Carnot engine, the efficiency eta, which is defined as 1 minus Q2 by Q1, or the way we started, it's W by Q1. It can be shown that this efficiency of the Carnot engine can be written as 1 minus T2 by T1. So if we replace the Q2 by the corresponding temperature of the sink T2 and Q1 by the corresponding temperature of the source T1, then this will be exactly the expression of the efficiency of a Carnot engine. So eta Carnot can be written as, so we don't have to be dependent on the heat exchange. We can directly calculate the efficiency of the Carnot engine by looking at the temperature of the particular sink. So we can write that eta will be 1 minus, so it will be T1 minus T2 by T1, so it will be 1 by T2 by T1. So the question is, how can again we maximize the efficiency of the Carnot engine. So it's very simple. If we keep the answer is straightforward. We have to just maintain a huge amount of temperature difference between the source and the sink, as simple as that. Because if we keep the T2 is very smaller than T1, then the corresponding ratio will be very small, and we can neglect this particular ratio with respect to 1, and we can neglect that, and this particular efficiency will be very close to unity. Now, as we have seen, exactly if we follow the similar kind of procedure, it can be shown that the coefficient of performance of a Carnot refrigerator, which earlier I have shown you, it was given as Q2 by W, which was written as Q2 divided by Q1 minus Q2. It can be very easily, it can be shown that the omega of a Carnot, so a Carnot refrigerator, it will be having a coefficient of performance is nothing but T2 divided by T1 minus T2. So what we have to do is basically we have to just replace the corresponding heats with the corresponding temperatures. So the sink heat, the heat is going into the sink with the corresponding temperature of the sink, and this Q1 minus Q2 is Q1 minus T2. That's how we can define the coefficient of performance of a Carnot refrigerator. Now let's define about there are two such statements of a second law of thermodynamics which will come into play. So there are two statements which are which actually look different, but they are basically the same. There are two such statements, and first statement is called the Kelvin-Planck statement, and the second statement is known as the Clausius statement. Both the statements are actually look little different, but eventually both of them, these two statements, are equivalent. They are the same. So let me tell you what the Kelvin-Planck statement says. It basically talks about the heat engine, and the Clausius statement, it basically talks about the refrigerator. So Kelvin-Planck statement says that we can't make in any kind of such a heat engine which will take the heat from the source and 100% it will convert to the heat, the mechanical output. So it means that they are saying that it's not possible to construct a heat engine which will take the heat from the source and completely convert it to the mechanical work without giving any heat to the sink. That's not possible. That's what is given depicted in the Kelvin-Planck statement of the second law of thermodynamics, as simple as that. So which means it has to have some amount of heat which has to go to the cold reservoir or the sink. We can't completely convert it from the heat to the mechanical work. 100% conversion is not possible. And then the Clausius statements talks about refrigerator. It basically tells us that we can't make any kind of a refrigerator whose performance will be complete extraction of heat from the cold reservoir and completely conversion and giving it to the hot reservoir. I mean, without any external performance of work on the refrigerator, it can't completely convert the heat. It can't completely extract the heat from the cold reservoir and completely giving it rise to the hot reservoir. I mean, it has to there has to be some amount of work which needs to be done on the refrigerator so that it will take the heat from the cold reservoir to the hot reservoir. Without any performance of the work, it can't perform alone. Means this particular thing is not possible. There has to be some amount of work on the refrigerator. That's what Clausius statement says. So that's all. With this particular lecture is concluded. Thank you.